This unit addresses Chapter 11.4, Perform Quantitative Risk Analysis. Quantitative risk analysis deals with determining which risk events warrant response. This decision is complicated by a number of factors, including, but not limited to, opportunities and threats which can interact in unanticipated ways. A single risk event may cause several impacts, as when a late delivery of an item produces cost overruns, schedule delays, etc. Opportunities for one stakeholder may be threats to another, causing stakeholders to work against each other. This analysis is based on quantity rather than qualities. We put numbers to the pain, such as dollar impact to cost, days delay, etc. There is, however, a risk that mathematical techniques used may create a false sense of precision and reliability. Quantitative risk analysis generally follows qualitative risk analysis, though the processes can be used together. Considerations of time, budget, and project need for risk management will determine which method or combination of methods to use. Primary driving information is the risk register, which lists the risks we are analyzing. We use the risk management plan to guide this process and make use of the schedule management plan and the cost management plan for managing the impacts. Enterprise environmental factors and organizational process assets can provide us with quantitative standards and historical information. The output will be added to the risk register, yielding project document updates. Look at the PMBOK guide for examples of distributions. We also discussed this topic in earlier units. View the diagram on page 339 of the guide as you read this. Follow along slowly. This is complicated but not rocket science. Initial decision node on the left, outcomes on the right. You start a decision tree with a decision that you need to make. Draw a small square to represent this towards the left of the large piece of paper. From this box, draw lines towards the right for each possible solution, and write that solution along the line. Keep the lines apart as far as possible so that you can expand your thoughts. At the end of each line, consider the results. If the result of taking that decision is uncertain, draw a small circle, chance node. If the result is another decision that you need to make, draw another square, a decision node. Squares represent decisions, circles represent uncertain outcomes, usually more decisions to make. If you have completed the solution at the end of the line, put a triangle, end of branch. If you have a new decision node, draw out lines representing each option that you could select. From the circles, draw lines representing possible outcomes with associated probabilities. Put a box on each line saying what it means. Keep on going until you have reached end of branch on all branches. Calculate the net value of each branch, which should point you to the best solution. This is a tornado diagram. It looks a little like a tornado, right? It shows the sensitivity of the outcome to the various factors listed. This chart shows calculation of expected monetary value. Basically, the formula is probability times impact summed over the different scenarios. The modeling picks random values from the specified range of potential values for each step independently, then calculates the schedule or cost for the project as a whole. The result is retained and another random set of values is selected and another run, and so on many times. This is generally not practical without the use of computers. The result is then displayed as a distribution of outcomes, total cost or schedule length, versus the probability of that result. The example cited in the guide shows you how you might use probability distribution to gain a quantitative understanding of the probability of each outcome. As an example, there are a number of tools which will use a Microsoft project file to simulate schedule or budget results using a specified range. How about the range of values in three-point estimates? This information can help to quantitatively determine what the project reserves should be, and the organization can decide how much confidence they want to have in the final number. This might lead to changed decisions on even doing the project. What probability of success would you want before you would agree to be launched into space in a NASA rocket? Don't ask an astronaut. They always want to fire it up. We have seen this one before. Makes sense to go to the experts for information on this one, doesn't it? An example would be a distribution of outcomes like the one on page 340. This turns the result around and asks, what is the probability of achieving the given project objectives?